Welcome to this lecture. In the last lecture, we are trying to classify the cohesiveness and the coupling existing between different modules, because that will give us a hint as to how good is the design, whether it is functionally independent or not. If it is a functionally independent design, then we will have a case of very high cohesion and low coupling. And in the last lecture, we had discussed that by looking at a module structure, can we identify what is the class of cohesion that exists in the module. There we looked at 7 classes of cohesion, and we said that by examining the functions in a module, we can say approximately that to which class of cohesion does the module belong, or the module has which class of cohesion. And then we are trying to do the same thing with respect to coupling between two modules, and we said that coupling is the degree of dependence between two modules, or the degree to which they interact or exchange data with each other. If there is no interaction between two modules, then there is no coupling. If they interact only by exchanging some very simple data items like a integer or a character, then there is very low coupling called as a data coupling. But if they interact by exchanging complex data like arrays, trees, lists, very complex structures and so on, then we called it as a stamp coupling. Now, let us proceed that can we by looking at the structure of two modules that are given to us, can we say that how good or bad is the coupling between these two modules. So, let us proceed from that point. We said that the coupling existing between two modules can be classified into 5 classes: data coupling, stamp coupling, control coupling, common coupling, and content coupling. Content coupling is the worst form of coupling, and nowadays the modern programming languages, they do not allow programmers to write a program where a module can have content coupling. Now, let us look at these different forms of coupling, and we will even look at the case of content coupling just to be aware of the issues involved. In data coupling, two modules they interact, but then they exchange only very simple data items. For example, just an integer or two integers, or maybe a floating point number, maybe some character and so on. And of course, one thing we must be sure that these are used like data members in the other module to which it is invoked, and this should not be used to set a control parameter in the other module. In that case, we call it as a data coupling. A slightly worse form of coupling is the stamp coupling. This is also easy to identify given a module structure. If we find that one module invokes another module and interacts by passing or receiving a complex data structure like an array, linked list structure, etc., then we say that it is a case of stamp coupling. A still worse form of coupling is the control coupling. Here the two modules pass data items between each other, but then the data item passed by one module is used as a control element in another module. For example, it may just send a integer which is used as a flag tested in another module. So, let us say we have two modules here, and let us say this module invokes a function, let us say f1, and f1 passes a let us say integer I, and here this integer I is let us say switch on integer I. One of the functions switches on integer I, and depending on the integer value I, it does different things. So, the value that is passed here is used as a control element in the other module, and this is also a bad case of coupling. It makes understanding the design very difficult, and we call this a case of control coupling. Another bad form of coupling is the common coupling. Here two modules are coupled, but they are coupled through some global data. Normally, if we have a module here and another module here, they have their own data, and the different functions here, they use this data here, the data that is defined in the module. And this module, let us say this module is M1 and this module is M2, and this module has some data that is visible within the module, and there are functions, let us say f5, fcx and so on. Now, they use this data, but sometimes we can have some global data here, and these different functions, they access the global data and communicate among by using the global data, and this is a bad case of coupling, where we have the modules communicating with the help of some global data, and this we call as the common coupling, and it is a bad case of coupling. Then we say that the modules are highly coupled if there is a common coupling. And the worst form of coupling is the content coupling, and modern programming languages disallow this kind of coupling. You cannot even write a code using modern programming languages where they do have content coupling. But earlier in machine language and assembly language program in old computers, it was possible to have two modules, they share code. That is, we have one module here and another module here, M1 and M2, and it is possible for M1 to execute some piece of code here, come back here. So, just because do not want to write this much code here, we just had a jump here to this module and used this code here, and then again jumped back. So, this is a very bad form of coupling. It makes understanding this module extremely difficult, and it is a bad programming disallowed in the modern languages. You cannot just jump into another module, execute some parts here. Let us say we have a function here f1, and you jump into the middle of this function and run few statements here, come back here. So, that form of thing is not permissible. Either you call the full function or do not use anything here. You can just jump into one module, run part of the function and come back. So, this is the case of a content coupling, and largely disallowed in modern programming languages. Now, let us look at the other aspects of a good design. One is the hierarchical design. Here, if we look at how the modules call each other and represent that we call as the control hierarchy. So, we say that this module, it calls these two modules, and these two modules in turn they call other modules, and this we call as the control hierarchy, and this is also called as the program structure, and typically represented by a structure chart. We will look at the structure chart in next couple of lectures, and this program structure is a tree like structure and it is hierarchical, and this is how a good design is organized. So, we say that a good design has a hierarchical module structure and it has a well defined control hierarchy. But then given a control structure, how do we say that whether the control structure is good or bad? For that we need to define two terms, fan out, abstraction, fan in, and so on. A good design should have low fan out, it should have abstraction. Let us see what we mean by that. Let us say this is a control structure of a application, this is the module structure, how they call each other, and depth is a easily defined term, that how many into how many layers they are organized or levels of control, and then width, this is the span here, and the fan out of every module is how many other modules it calls. For example, M1, the module M1, the fan out is 2 here. For module M2, the fan out is 3 here. For module M3, it is 0. So, the term fan out says how many other module it invokes in a hierarchical structure. Now, what about fan in? Fan in is how many different modules call this module. For example, here the fan in of every module is 1, but let us say we also had M3 calling this, then the fan in of module M6 will be 2. Now, one thing to remember is that a very high fan out, let us say this is 3, we can have a case where there is let us say 5 or 7. So, sorry, if M2 calls let us say several modules, then we say that 1, 2, 3, 4, 5, 6. So, the fan out of module M2 is 6. A high fan out is bad because M2 is depending on too many other modules, and it is a hint or it is likely that M2 has a very bad cohesion. It is just doing too many things, and that is why it is needing many modules. A high fan out is bad, but a high fan in is a good thing, because there are many modules which are depending on M5. Let us say there are other modules also which are depending on M5. So, a high fan in is good because it means that we are able to achieve reuse of code, and that is a good design. High fan out is bad, but high fan in is good. This is an example where the fan out of this M1 is 2. For this M3, fan out is 1 and fan in is also 1. For MC, fan out is 0 and fan in is 2. A good design structure, we can compute the fan in and fan out, and if we have a very high fan out for some modules, we will say that it indicates that the design lacks cohesion. But if there is high fan in, then that is not bad, it is actually a good design if there is a high fan in and a good reuse can be observed in that application. A large fan out, as you were mentioning, is that it is an indication that a module having a very large fan out is doing very different things. Its cohesion will be poor because it is needing too many other functions, it is invoking them different modules. There are few other terminology with respect to the control relationship. We say that M1 is superordinate of M2 and M3, or we can say that M1 controls M2 and M3. In other words, we can say that M2 and M3 are subordinate of M1 and M4, M5 and M6 are subordinate of M2. M1 calls M2 and M3 and therefore, M2 and M3 are visible to M1, but M1 is not visible to M2 and M3. M2 the visibility is M4, M5, M6. So, we say that the superordinate modules, they are actually abstractions of M2, M3, they are not visible here. M1 is the most abstract module and M4 is the most concrete module, and this is a layered structure. First of all, to have a good design, we must have a layered structure, that is the control hierarchy we should be able to organize into distinct layers, and then we can identify the fan on, fan in, fan out and so on. This is a bad case of the design. First of all, there is no layering, and also it is not a simple tree like structure, and it violates the principle of abstraction. For example, M5 is the most concrete module, M4, M5, M6, and they should not be able to see the higher level modules M1 etc. They should not be visible here, but see here M5 is invoking M1. So, M1 is visible to M1, M5. So, this will be a very bad case of design where it will be very difficult to debug, because just see here there is this cyclical relation here. Given a bug, we can just go round and round and still not be able to trace the bug. But if it was a strict tree like structure with layering, if we observe a bug here, then that is either here or with its subordinate modules. So, understandability, debugging, reuse etc. are facilitated by a layered design, and if we have a design like this which violates the principle of abstraction and layering, it is a case of bad design. In a good design, the modules are layered, and the top level modules here, the abstract modules, they do more managerial function. They just invoke the lower level modules to do some work, and they in turn invoke, these are the middle managers, they invoke other modules, and the lowest level modules they do input output. So, the input output data, they do some processing here. So, M1 calls M2, M3 and these do some processing, get data from M4, M5, M6 and do some processing and pass it on to M1 and so on. In a good layered design, a lower level design should not be able to invoke an upper level design, and that is invisible. that should be invisible to the lower level modules. We can therefore say that if we write a program or we identify that a set of functions f 1 to f n are to be written, and then the task of high level design is to organize that into a module structure. We should be able to assign these functions to different modules such that each module has high cohesion and there is low coupling among modules, and also they are organized in a tree like fashion. And this is the crux of the procedural design approach. Even the object oriented design approach, this principle is used. So, here observe that we identify what are the functions in our applications to be written, and then these functions are organized into different modules such that each module has high cohesion and low coupling among modules, and also these are organized in a nice tree like fashion. We will look at a methodology, I think within a next lecture, next to next lecture, where we will do a procedural design. We will identify the functions here by using a data flow diagram, a structured analysis principle, and then by using a structure chart, structured design, we will be able to come up with this module structure and a tree like diagram. Two design approaches are popular. One is the function oriented design and the other is object oriented design. Given that we know now by now that what are desirable of a design, that is, this should be functionally independent, tree like structure, layered, and so on. We will look at two approaches, the function oriented design and object oriented design, to arrive at a good design structure. But before we look at the nitty-gritty of these two design techniques, let us have some very overall understanding of what is involved in function oriented design and object oriented design. These two design techniques, even though popularly they are believed that they are competing approaches, but not really. As we proceed, we will see that they are complementary approaches, because object oriented design also uses the principles of procedural design. So, it is not that the object oriented design technique has made the procedural design redundant, no, sorry, the procedural design technique are also used as part of the object oriented design. We will examine those issues. First, let us look at the function oriented design. Here, by looking at the description of the problem, we will identify the set of functions which this needs to perform. Once we identify the set of functions, then we will map this into a module structure. Identifying the set of functions to be performed is called as the structured analysis, and then this set of functions will identify into, will map it into a module structure, and that module structure will, arriving at the module structure, we will call it as the structured design. We will also call it as the top down principle, because initially we consider the system as performing a very small set of gross functions or very large granularity functions, and then we will split these into small functions. We will successively refine into more detailed functions or smaller functions, and then there will be a large number of functions, and each of those we will map into the module structure, and that is the reason why it is called as a top down decomposition principle. As we will study these function oriented design techniques in more detail, it will become clear why it is called as top down decomposition. Once we achieve the top down decomposition, we map the function structure into a module structure. Just to give an example of a top down decomposition, let us say in a library software we have a function named as create new library member. Now, we can see that the create new library member requires some activities to be performed. For example, we need to first create a record for the new member. We will have to assign a membership number and also we will have to print a bill towards the membership. So, we can consider that the function create new library member to be consisting of smaller functions or sub functions, that is create record, assign a unique membership ID and then print bill. Similarly, for every function we can study that what are the activities to be performed under that, and we can split that into simpler set of functions, and we can do that recursively in the sense that we can again look at the sub functions and find if this can be split into still simpler functions. And that is one of the important principle of function oriented design, that we look at what are the functions that the system performs and then split those into simpler functions. And the other thing that to notice about function oriented design is that all these functions, they operate in some centralized data structure. For example, in a library system, all the functions may be needing to operate on the set of books or the set of member records and so on. So, these are two distinguishing characteristics of a function oriented design, that we need to identify the functions that the system performs, break those functions into simpler functions, and also identify the data that are centralized, and all these functions operate on that. We will take one example and see how do we go about doing the function oriented design. And of course, later we will look at this technique in more detail. We will look at the data flow diagramming technique to do the structured analysis, and then we will take the structure chart and see how to do the structured design. We will stop here and continue from this point in the next lecture. Thank you.
Hello everyone, I am Nitika Arora, Assistant Professor of Computer Science from Shaheed Udham Singh Government College, Matak Pachri, Indri. Today the topic is classification of coupling. So आपने coupling के बारे में वीडियो में ऑलरेडी देख लिया है, जिसमें हमने टाइप्स ऑफ कपलिंग डिस्कस की हैं, कपलिंग की डेफिनेशन है, कपलिंग का क्या पर्पस है. तो लेट्स स्टार्ट विद द क्वेश्चंस. Question number 1, define coupling. So you have to explain the coupling. Question number 2, what should be the ideal combination of coupling and cohesion? तो coupling और cohesion को बैलेंस करने का ideal combination आपको बताना है. Question number 3, what are the characteristics of module structure? Question number 4, explain the classification of coupling. That means name the types of coupling. Question number 5, define content coupling. So discuss about the content coupling here. Question number 6, what is function oriented design? Question number 7, define bad design. Bad design के बारे में आपको बताना है. So these are all the questions based on the topic classification of coupling, and discuss with your class teacher and then write down the answers of all these questions. Thank you.